Alright, hey guys, what's going on? So today we are going to be talking about Feynman diagrams and using those Feynman diagrams to actually calculate some scattering amplitudes. So without further ado, let's get right into the content. Alright, so we are jumping into using Feynman diagrams for calculating scattering amplitudes. And so we're going to start off with a zeroth order approximation of what's going on when two particles are coming towards each other, or they're actually not coming towards each other in this case, because a zeroth order approximation is an approximation in which there's no interaction at all occurring between the two particles. So what does that look like? So here's our zeroth order approximation. That's what the zero in the superscript stands for. And this actually applies to all the possible Feynman diagrams that in which the particles do not interact with each other, right? So we have this diagram, and this diagram. The difference between this diagram and this diagram is the different space-time placements of the two momenta. And we want to sum all of these up, okay? And let's see what happens. So we have our first one here, so we have our line going from K1 to K1, that's this one, and then from K2 to K2, right? So no interactions taking place, two completely parallel lines. Here we're going from K1 to K2, so K1 to K2, and then K2 to K1, K2 to K1, and then here, same thing, just different space-time points again. So what does this look like? So the two, for K1 to K1, K2 to K2, we have two right here because these are the same. If we're looking at this algebraically, these two things, there's two of them essentially, so multiply that by 2, and we have this guy here, which is this guy. And then what we're going to do is we say this guy right here is 2, so we carry the 2 out, and we're using our important contractions, right? So our important contractions are, we have this guy here, or sorry, this guy, what I'll underline in blue, is this right here. And I'm realizing now there should be an E at the end of the line, just a spelling error. And then this guy here corresponds to this line right here. And if you're having trouble understanding why this is the case, you can go back to my videos on important contractions to see exactly why we make these substitutions. And these, again, are just normalizing constants, right? So, again, this process here corresponds to this arrow here, and then this algebraic statement here corresponds to this arrow right here, right? So, the two important videos that you want to go back to, if this is something that you haven't seen yet, are, again, the important contractions video and the Feynman diagrams video, where we talk about what exactly the Feynman rules are for the model that we're using. Anyways, let's continue. Then we have this guy here that corresponds to, I'll do a different color. This guy here corresponds to this guy right here. And then in a different color, I'll do pink. This guy here corresponds to this guy right here. And we can see that this guy goes to 0 because K1 and K2 are not the same. Same thing here. So these guys go to 0. So we're left with this term right here. What is this, right? So 2, so we have square root of 2 times square root of 2, that's just 2. Square root of 2, square root of 2, that's just 2. So 2 times 2 times 2, well, that's going to bring us our 8. All right, so that's something that we've calculated before when we were going through Wick's theorem, right? Wick's theorem was the long way of doing this. Feynman diagrams are the short way of doing this. And then we have square root of K1, square root of omega K1, that's just omega K1. And then same thing here, we have our omega k2s. And then 2 pi to the third, right? This should be, let's see, 2 pi to the third. We should have that outside of the exponent. Right, and then, so we have 2 pi third, 2 pi third. Well, that's going to be 2 pi to the 6. And then, this at 0, right, that's going to be 1. But this would, recall, when we went through Wick's diagram, or Wick's theorem again being that the contraction between two fields is the difference between the time order and the time order and the normal ordered product of the fields. If we go back to that video, we could see that this is the exact answer we got from using Wick's theorem. But we're not using Wick's theorem in this case, we're using Feynman diagrams. So in the one hand, we can go through the long, arduous calculations of Wick's theorem. And what the benefits, though, of Wick's theorem is we can really get an understanding of what's going on. We can get an understanding of what field contractions are and all that kind of stuff. We can really understand the back-end calculations that go into this. Feynman, on the other hand, he gives us a very good tool so we could skip over that. So if you're someone who really wants to understand the back-end calculations, Wick's theorem is there for you. If you're someone who just wants to get your homework done or just move on, then Feynman diagrams are your friend. Anyways, let's keep on going. So we're going to do the first order approximation now. The first order approximation, again, we have our incoming lines, right? So this is our first order approximation with the 1 in the superscript, right? So we have these incoming lines here, and so we have incoming line K1, that's this one, K2, that's this one right here. What I can do is I can say, K1 is this guy. So we have our incoming line K1, and then we had our incoming line K2 right there. And then our vertex point, and then we have, I'll do a different color here, our outgoing K1, and I'll do a different color, purple, how about purple? Outgoing line K2 right there. And then when we apply the Feynman rules, again, that we went over this already. This is our incoming line, outgoing, and outgoing in our vertex. And we integrate over space-time because we're integrating over that volume the volume in which they're interacting. And we can see that everything's going to cancel, right? Because this whole thing is a negative exponent, and that's going to cancel with this guy, right? So that's going to cancel, and then these two guys are going to cancel. And what we're left with is a constant I lambda, and that I lambda can get brought outside of the integral because that's just a constant, right? That's just a constant. So what we're left with is this, and when we integrate over space-time, we get our volume of space-time, our space-time volume. So, and this is the exact same thing that we get with Wick's theorem. So far, so good. It looks like Feynman diagrams are really, this is a very quick calculation for going through this kind of stuff. Now let's do the second order approximation. All right, so the second order approximation looks like this. Okay, and what we have going on here, well, let's see here. So incoming line, that's these two guys. Then we have propagator and a propagator. We have two of them because we have two lines. Then we have outgoing line and outgoing line, right? So those are these guys right here. And this is just one of many second order terms, one of many terms in which there's two interactions going on, right? There was another one where we could have done, again, something that looked like this, but I'm just going to calculate, I'm just going to calculate this one for right now because doing something like this again. We can do it. It's just a longer video. I just want to give you the gist of how this works. Right, so let's do this now. So, okay. Oh, and then we have our vertex points, right? So we have squared because there's two vertex points. All right. So negative I squared, right? That's just going to be 1. Okay, so let's see, how are we going to do this? So here's our incoming lines, outgoing lines. We replace, so these are our Feynman propagators. This is something we covered way back when, what exactly these propagators were, right? So we put these guys into these two guys. And we have to make sure they're different, right? We have Q and P. Q and P. The Q and the P represent four momenta, again, but they have to be different because these two lines might have different momenta, okay? And so where does that take us? Right, so we have, again, we're integrating over two space-time coordinates, right? Because we have K1 at x1 and K2 at x1, right? So that is at this x1 point right here. And x2. So that's where those guys come from. And so we have those two. So here again, I'm down here. We take these guys outside of the parentheses, right? So we can go ahead and take those guys out because everything's just an integral. And then we integrate over all these independent variables. And then, right, so this guy right here is taking K1, K2, right? So these are our x1 points. So K1 and K2, and then our P and our Q, right? So if we FOIL things out, what you'll find is that you get this P and this Q here, and minus P and minus Q here for the second space-time point. Also, just the difference here is that we have a K3 and a K4. All right. Okay, so we've covered this guy. What about this guy right here? Well, these guys are the two denominators right here, right? So this is just rearranging a few things. All right, next step. So we go, let's see here. So if we integrate over x1, right, this is what we get, right? Because this is essentially Fourier series, right? We have some frequency, or some complex frequency, and we get a spike at that frequency, right? So the delta spike at whatever frequency this form is, right? So here, I'll just underline this. So we have this guy here, and this guy here, this guy here, and this guy here, right? So if I do red, and purple, and then we have these normalizing factors outside that we've talked about in the past, where this is just, again, this is a Fourier series, so I'll just underline those guys also, just to be complete. And we've done nothing else, right? We've done nothing else. We haven't done anything to these guys yet. Okay, and we haven't really done anything to these guys yet either. Okay, so now we want to get one momentum, right? So we have two momenta. If we want to get one momentum, let's go down to this picture really quick. We have our two incoming particles. We have our two outgoing particles. We have our two space-time points at which they're interacting. And what we're saying here, what we're going to say right here is that we're essentially replacing P with K1 plus K2 minus Q. Now, why are we able to do this? Well, here's P, we're saying K1 plus K2 minus Q. Well, if we add Q to both sides, P plus Q, well, that's the same thing as K1 plus K2. So this is really a conservation of momentum statement. Right, so what we're doing right here is just stating a conservation of momentum, a universal fact about the conservation of momentum. Right, so that's what this replacement is doing. So now everything is in terms of Q, which is great. Right, we'll do the same thing here. And so now that everything's in terms of Q, this is our answer. So we're left with trying to integrate this thing. And what we're going to do in the next video is integrate this thing. And it's going to be super quick because what the book does is it says we are going to leave it to the mathematicians to do this integration. So, and that's what we're going to cover in the next video. And what we're going to find is something very, very interesting because I'll allude to it right now. This Q right here can take on an infinite number of momentum values. Right, so you can imagine you have two particles, each have some momentum, and they come at a space-time point. Now, the only rule that we really need to abide by is that the momentum at this initial state and the momentum at the final state, here, I'll draw this as a picture maybe. We have, say this is our final state, and our two particles in our final state, and say this is our initial state, our two particles in our initial state. And then here's our black box. Okay? So, final state particles, initial state particles, right? So, this is what our Feynman diagram looks like. What goes on in here, in this black box, the two things have to conserve the momentum, right? But nothing's really stopping us from saying that things temporarily could get really out of hand inside of this black box, right? Because again, these two momentum here just have to equal these two momentum. Anything really goes inside this black box. It's a black box, right? So we could have extra particles coming in and out of existence, right? That would be extra particles contributing to the momentum. So what happens in here doesn't necessarily have to obey the conservation of momentum. And so this is a problem, right? And that problem is going to be rectified by something that we're going to call the renormalization coupling. And this is going to help us put a threshold on exactly what goes on in this black box, right? And it's going to be in terms of our initial state particles. And we're going to cover that in the next few videos. And this is very, very important process because this takes us to different areas of physics, such as conformal field theories and topological field theories. This idea of renormalization or renormalization coupling is very, 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 very important, and we're gonna spend maybe 1 or 2 videos on it. But anyways, that's the point here. The point is that the only things that have to happen is momentum conservation between here and here. Right? What happens in here doesn't necessarily have to obey the conservation momentum. So, with that being said, I hope you guys like this content. Please make sure to hit that like and subscribe button, and I will see you guys in the next one. Bye.